is our first unit. We're starting calculus right away. It's on limits. And the concept of a limit is something that you can get as close to as possible. Anybody else not have the note package yet? And so your first idea of a limit probably came in grade 11. And you had geometric sequences in series. So for example, if I start 16 blocks away from the wall, and I walk half the distance to the wall, I'd be 8 blocks away from the wall. And then if I walked half the distance again, I'd be 4 blocks away. And then I walk half the distance again, and I'd be 2 blocks away. And half the distance again, 1 block. And I could do that forever. Just keep cutting in half and getting closer to the wall and cut in half again. Would I ever get to the wall? No. But the concept of the limit is, if I kept doing that forever, I could get as close to the wall as possible. In fact, you learned in that unit that if you added up all those halves, it makes a geometric series. And back in grade 11, you had a formula for a geometric series. If you added them all the way up to infinity, it was term 1 over 1 minus r. And if I put numbers in for those values, eight divided by half is 16, which makes sense. I started 16 blocks away from the wall. If I did that forever, I get arbitrarily close to 16, so close to 16 that at infinity, you would say you've basically got to 16. Even though technically you never reach that, 16 would be the limit that I would get. I never go past 16, but I could get as close to 16 as possible. So here's this concept of a limit that becomes very important in calculus, because sometimes we want to see what happens when we get close to something, especially something we're not allowed to get close to, like a non-permissible value. What happens to this function as we get close to 2 if 2 is a non-permissible value? So we separate our calculus that we're about to learn into 2 major sections. There's derivatives and integrals. And so this first part that we're looking at is differential calculus. A little historical stuff about them. Now we almost always learn differential calculus before we learn integral calculus. But integral calculus was sort of discovered way earlier, and it's used to find areas under curves. So if you wanted to find an area of a rectangle, you already have a formula for that. Area of a triangle, you've learned formulas for that. You learned areas of circles. But sometimes we have weird shapes, like parabolas. Here's a parabola. Find the area under that parabola to the x-axis. Well, the problem is that's curved. You know how to find rectangles, but you don't know how to find that curved shape. Or I can make any curved shape. What we're going to find out in integrals is we can find areas of any kind of shapes, not just the ones that we had formulas before. And it uses the idea of a limit, because the idea that started it was Archimedes way back, and he said, well, I can't do that curved shape, but what if I made little tiny rectangles and added them all up? Wouldn't that be a close estimate for what is actually the area under that curve if I just broke it up into little rectangles instead of bigger shapes? And then he said, well, if I keep making them littler and littler, smaller and smaller, every single time, I will get closer and closer to what the actual area is. And so he applied this idea of a limit. At that time, he called it a method of exhaustion. because I want to find one area, so why don't I find the areas of a million little rectangles? Wouldn't that be exhausting? And add them all up. But I can get closer and closer. So Archimedes, way back in 300 BC, father of integral calculus. Differential calculus, with what we're doing right now, has been associated to both Newton and Leibniz. Now, Newton was in England, Leibniz was in Germany. So it used to be, if you were studying calculus in the early 1900s, if your textbook was in English, your textbook would say Newton discovered calculus. If your textbook was in German, your textbook would say Leibniz discovered calculus. It's now accepted that they both discovered calculus independently at roughly the same time. I mean, there wasn't the internet. So if someone found it in England 20 years before someone found it in Germany, or vice versa, it wasn't really like one influenced the other at that time. So they both found it and worked with it sort of simultaneously, and they're both credited with discovering calculus. So our first thing that we're going to do before we get into limits is we have to develop some of our skills with factoring. I've included some of my favorite trinomials here. This one I really like. Why do I like this one? Okay, it's factoring. It's a basic one. You, by now, are probably pretty good at factoring. Sometimes I'd like you to go back, if I have a grade 10 class, I like to bring my grade 12 class in, and just when they're starting factoring in grade 10, just sort of say, are you going to use factoring in math from grade 10 to grade 12? The answer is yes. You will use it a lot. So hopefully you learn it well in grade 10 so that you can do it later on well. Now the reason I like this one is because what two numbers did your gut tell you to use first? Sorry? 12 and negative 2? Anybody's gut say 6 and 4? Yeah? Good. Well, both 12 and 2 and 6 and 4 make 10, right? So that's why I like this one, because it's not obvious right away which one it's going to be. The answer, of course, is 12 and 2, because that's the only way you can get the negative 24 and the positive 10. But this one, the 6 and the 4 also give you 10, so depending on, but if you tried the 6 and the 4, you can't get the positive 10 and the negative 24, right? Because if I try to get positive 10 with 6 and 4, they both have to be positive. But then when I multiply those last ones together, I get positive 24 instead of negative 24, so then this one doesn't work. One thing I hope you do with factoring is after you factor something, do a quick check. Do my last terms give me negative 24? When I multiply this completely out, does the outside and the inside give me the 10 that I need? So one thing that I don't always, I try to do it when I'm doing my work, but it's not always apparent, and I want you to start thinking about, is each time you do a step in mathematics, you should do a quick mental check. Is that same as what I had above? Because if you're doing that all the way through, you're going to catch some of those errors, and you don't want to like work for 5 minutes on a question and find out, oh, I made a mistake in line number 1. So I've wasted all of that time. Anyways, I like this factoring one because it can be more than one thing. But that's a pretty straightforward review. We also have things that sometimes have a common factor. So in this one, you can first pull out the h and then have to factor the binomial in the inside. Now, over the years, whenever there's a number in front of the thing that's squared, sometimes people find those ones are more difficult. I'm going to talk a little bit about some strategies that I use sort of as shortcuts when factoring these. You might have learned a grouping strategy or other strategies along the way, and those are great. But for the most part, I want you to go directly from this to factoring it. And some of the strategies that I like to use when going directly and factoring is noticing what happens with your first and your last term. Yes? The one would be negative. I just made a mistake. Thank you. I'd like to say I did that on purpose, but I didn't. That's where I just had in the video, always check your work in the next line, and then I didn't do it, and it would have been disastrous. Okay. So here, I look at the first one and the last one because your first one's here and your last one's here always have to multiply to get that first and that last one. So when I look at 3h squared, if this is factorable, the only possibility for that is if you had a 3h and an h, using whole numbers, of course. So you can start with that, because you know if it's possible, that has to be that. And if my last one's a -1, not worrying about the signs yet, if it's a 1, the only way I can get 1 is 1 and 1. I've had no options so far, and I'm almost done factoring. Now, in order to get a 7, my outside and my inside would have to add or subtract to get 7. At this point, we should be able to see that this is not going to happen. There is no way to get 7 with the outside being 3 and the inside being 1. So at this point, we could say, I can't factor it any further. This is all I could do. You could apply the quadratic formula for something like this to check if there's a way to solve this. But at this point, we're just trying to factor. So all we can do is take out that common factor, and we would be done. Remember, differences of squares. So I know that some of you are coming from French immersion. Don't worry. I will help you with all the terminology. Most of the words are going to be easy to figure out and are going to be like, what did you say for differences of squares? Yeah. So the words are very similar for a lot of cases. There are a few cases where the words from French immersion to English are a little bit different, but they're not. You've probably even heard of the inverse and reciprocal one already. Mr. LaFrance probably talked about it because it's the worst one, right? Reciprocal in English is inverse in French, and inverse in French is reciprocal in English, and it's all messed up. But other than that, most things are the same. Now, a difference of squares is exactly that. There's a difference sign or subtraction. And both of these numbers are square numbers. Yes? It doesn't work with a positive. Because the reason it works, one of them is positive, one of them is negative, is you still have your first ones matching up with this first one. You still have your last ones matching up with that last one. But when you put the outside and the inside together, one's a positive 15x, one's a negative 15x, they disappear, and it's basically like you have 0 in between, which is why there's only 2 terms. And some people would say, well, we could factor this the same way as we factor a trinomial. But we get to recognize these and remember that as a shortcut. It does lead up to something new that we're going to learn. So far, this is all factoring, that's review. In a bit, we're going to learn how to factor sums of cubes and differences of cubes. And those are things that you probably haven't done before, or formulas you haven't seen before. This is also something that you probably haven't seen much of before. How do you factor something when you get not nice exponents, like negative exponents or fractional exponents? So what we're going to do in this case is we're always going to factor out the smallest exponent as a common factor. So in this case, it would be the x to the -2. If you factor that out as a common factor, And they don't teach this to you early because when they're teaching you common factor, someone would say, well, there's no x to the minus 2 in the 1. Well, you're right. But that doesn't mean you can't factor it out of a 1. What would have to be here? What would I have to multiply x to the minus 2 by to get a 1? It would have to have an x to the 2. So yes, technically, x to the minus 2 isn't a factor of 1, but you can still make something work. And then if I take an x to the minus 2 out of a 5x to the minus 1, I'd be left with a 5x to the positive 1. And finally, that x to the minus 2 is easiest to pull out of there. Everybody's okay with, negative exponent? That's really 1 over x to the 2. So I would need to multiply. I'd have to have an x on the top in order to get an x to the minus 1 there. And now what we have in the brackets is something in a form that we've seen before. And we can factor that. That was kind of fun. Negative exponent factoring. Same thing can happen with this one. I'll let you try this one. Now, you didn't necessarily need to see that you needed to bring the 3 out in front right away. Did some of you just start with pulling out the x to the negative 1/2? That's fine. But as far as a common factor, with each term, do you see that there is a 3 in each one? So you could have pulled out that 3 early on as well. Pulling out that x to the minus 1/2, there we go. Pulling out that x to the minus 1/2 would leave you with an x to the squared, a minus 2x, and a minus 15. And then that factors nicely to x plus 3, x minus 5. So we're kind of bending the rules of factoring. And that's okay. Because there are some things in the past that you would have said, oh, I can't factor x squared minus 5. Well, you can't factor that if you only use whole numbers. But if you want to bend the rules a little bit, why couldn't this be a difference of squares and have a square root of 5 there? That's perfectly fine. In fact, if you were solving this equation, you would have never solved it with factoring, right? You would have solved it by moving the 5 over and then square rooting both sides and getting plus or minus 5. But factoring it by bending the rules works the same. So you can do those sort of things. In fact, that's the beauty of algebra, is saying if it works for one number, it works for all numbers, and then we can really start playing around with things a little bit more. Some other factoring things, factoring cubics. Do you remember the factor theorem, the remainder theorem, synthetic division? So we can factor this using that idea. A reminder of the factor theorem. If you plug a number into here and it's equal to 0, that tells you that it's a possible factor. And knowing something about factoring also tells you that if I could factor this completely, these last numbers, when they get all multiplied together, have to equal a negative 10. So as far as when you're checking to find out what could be a factor, what you want to do is only check numbers that are factors of 10. So it could be plus or minus 1, or plus or minus 2, or plus or minus 5, or plus or minus 10. As far as doing the mental math, usually you like to start with the smaller numbers. So you could try, what does f of 1 equal? Well, that would be 3 plus 4, which is 7, minus 9, negative 2, minus 10, negative 12. Well, since that's not equal to 0, we know that x minus 1 is not a factor. But if we try f of negative 1, we're going to get a negative 3 plus 4 plus 9 minus 10, which is equal to 0. And any time if you plug in a number and it's equal to 0, this means that x plus 1 is a factor. In fact, we know that one of these is going to be an x plus 1. And so once you've discovered that one of them is a factor, what you did in grade 12 is you could either use long division or synthetic division. If you're using synthetic division, dividing by x plus 1, you put the opposite sign here. You write out all of your coefficients. So we went from 3, 4, negative 9, and negative 10. Bring down the 3, multiply. So you see what I'm doing here? This number multiplies by this number to get that number. And then you add these together, we get 1. Then you take this number now and multiply it by this number. Add them together. And finally, this number times this number. And we get a remainder of 0, which is what we expected. But these numbers that we have at the bottom now tell us that our original function, f of x, is going to be equal to our factor, which was x plus 1. And then what we're left with is 3x squared plus x minus 10. Going to factor this further. Well, if I have a 3x squared, if it's factorable, this has to be a 3x and an x. I'm going to see if I can figure out a way to get 1 in the middle. If I put a 2 here and a 5 here, my outside makes 6, my inside makes 1. So if I were multiplying that out, it is possible to get a 1. I would want my outside to be positive, to be plus 6, my inside to be negative, to subtract 5. And I do a quick check, negative 5 times 2 still gives me negative 10. And that's factored completely. Little cartoon here just for fun. Can you read that from the back? Halloween costume list, scariest costumes I could think of. Vampire, zombie, math teacher. Long division gives me the willies. All right. And here are some new formulas for you that come up when factoring. So you've learned difference of squares. We also have a way to factor a difference of cubes and a sum of cubes. Now, this year you have no formula sheet. And you have to know all of your formulas from previous years. We review them as we go through. We introduce some new formulas. You're going to have to know those as well. So sometimes we have to come up with, well, what is a strategy that I could use if I forget a formula? And for something like this, what I might do is take a simpler difference of cubes, if I've forgotten the formula, like x cubed minus 8. I'll make that equal to f of x. And I use a little bit of the strategy that I had with synthetic division and the factor theorem. Is it easy to see that f of 2 is equal to 0? That means when I factor this, I'm going to get an x minus 2. If I use synthetic division with x minus 2, I'd have a 2 there. I have 1x cubed. I have 0x squared. 0x's and a minus 8. Bring this down, multiply, add, multiply, add, multiply, add. And I get x squared plus 2x plus 4. So now if I apply this idea to my difference of cubes with x cubed minus y cubed, I notice that I had x cubed minus 2 cubed. So I got x minus 2. That's how I could get x minus y. I know that I want to get an x cubed. The only way to get an x cubed means that there has to be an x squared there. If I look at my last ones, I know that my last one here is a y cubed. And it's a negative y cubed. The only way to get a negative y cubed is if the last one here is a plus y squared. For the one in between, that's where using the example is nice. I found out, oh, it's plus 2x, and that 2 is right there. So that might help me figure out that that's plus xy. Again, once you get that answer, you could multiply this out and see, does everything cancel out? And you can see with the positives and the negatives, can you see, for example, the x times the xy and the negative y times the x squared cancel each other out. Both of them will be x squared y. But one will be positive and one will be negative. So, one of the skills that we like to have as a math student is the ability to forget, which you don't necessarily want. You'd like to have a good memory, but rediscover. So how do I use strategies if I forget this difference of cubes formula, but I still recognize it? How can I take a simpler example and use stuff that I've learned previously to help me figure it out? And there's also a sum of cubes formula. Notice that they're the same, but the negative happens here so that things can cancel out when you multiply them out. Well, we did this one already. But using the formula, you'd say, well, it's going to be x minus 2. It's x squared plus x times y, and this is x cubed minus 2 cubed. And then y squared. And I'll give this one for you to try. So sometimes it makes sense to rewrite it as actual cubes. So the second one being 27b to the 6th, that's 3b squared cubed. And then for the sum of cubes, you'd have a plus 3b squared. This is what I'd need for that first one to get a cubed. This is what I would need for the last one to get me the 27b to the 6th. And there'll be the negative sign in between.